So hi and welcome to tutorial 1087, Protecting Workloads on AWS. So my name is Stephen Mogg, I'm a Public Cloud Solutions Architect here at SUSE, and I'm excited to be joined by my counterpart at AWS, David Rocha, who's a Partner Solutions Architect on the SUSE Alliance over there. So in terms of what we'll be covering today, first I want to set the scene around SUSE, AWS and high availability, and then start a walkthrough of some of the HA technology, and we'll finish up with a few tips and tricks around HA for those customers that are already running it on AWS. So SUSE have a partnership that's stretched back well over 10 years. And over that time, there have been a number of milestones. And as you can see by this slide, there's been a large amount of activity and success in that time. In fact, we've probably helped thousands of customers move to the cloud. And it pretty much all started back in 2010 when SUSE Linux Enterprise Server was the first commercial Linux available on the AWS Cloud. And a few years later in 2015, we had SLE HA SAP available on the market.
And Stephen, I want to add that it's not even just the rich history between SUSE and AWS. Just in the past year and a half, SUSE is integrating over 65 AWS product or feature launches. And this includes a number of instances that we launched to host these mission critical workloads. Even looking at reInvent 2021, we've launched the EC2 R6i or the Amazon EC2 R6i and the M6i instances that launched with SUSE support. And these instances give about a 15% better compute to price performance and up to a 20% higher memory bandwidth per vCPU. And this is in comparison to the previous generations of those instance types.
Thanks, David. So we're talking about SUSE high availability today. And today I just want to point out that probably the easiest way to get the SUSE high availability software on AWS is to actually look at SLE HA SAP, even if you're not running any SAP workloads. Now, we are looking together with AWS to find better ways to provide it, but in the meantime, SLE HA SAP offers two key features which helps customers looking to run clustering solutions on AWS. The first one is, of course, the SUSE Linux high availability software, with the second being an extended lifecycle, which provides 4.5 years of support for each service pack we release. So if you are looking to protect a complex application, then there's no pressure to perform those annual service pack updates. So before we talk too much about HA services, I actually wanted to cover briefly the differences between HA and DR. So for me, HA, high availability, is about keeping a service, for example, a compute instance or a database, keeping that service as available as possible, and that usually happens within a single region. Now, HA is typically automated, so there'll be some kind of intelligence which is monitoring the services to see if it's up and running or to check if it's failed. And then there'll be a process sat behind that which is invoked in order to restart the service or move it to a different node as needed. With regards to disaster recovery, as the name suggests, it's for when disaster strikes. Now, it's usually an outage which affects multiple services. And the key difference is that usually it's a business decision to invoke DR. So there'll be a DR committee or a management meeting which decides to take that move rather than something that happens automatically. Whereas HA, it definitely is automatic. Now, as some of you may know, SUSE's HA solution effectively works by building Linux clusters. And on this slide here, we've got two nodes represented by the large grey blocks. And on premise, those Linux servers would be in separate racks, potentially on separate floors, maybe even separate data centers if they're close enough and the latency is low enough between those two sites. There's typically an application running on the cluster, and a virtual IP address is often used in order for the clients to connect into that service. Now, during a failure of a node, either whether it's a rack or the data center, depending on how your cluster is designed, both the application and that virtual IP address will be moved or restarted on another node within the cluster itself. Now, the blue blocks represent the SUSE HA components. So at the bottom of the stack there, we have something called Corusync. That's a service which manages the cluster nodes themselves and the cluster membership. Above that, we have Pacemaker, which is our decision maker or our policy engine and decides what to do in the event of a failure. The third thing there are resource agents, and it's actually these are quite key. So they provide some of the intelligence in order to stop and start and monitor resources. Even things like IP addresses, all the way up through to complex databases, will all need some kind of resource agents in order for them to function. And the last bar at the top is about is fencing. So as you can see, we've included a little bit of shared storage in the small grey box at the bottom. And shared storage is often used by the cluster as a secondary way to communicate. So in case there's a network partition, which is where the nodes either can't see or communicate with each other, it's a way to ensure one of the nodes is down before safely starting those services elsewhere. After all, if you had both nodes thinking they were the only node remaining in a two-node cluster, and then each node started that service or mounted file systems, it could lead to data corruption. So on premises, fencing is traditionally handled by using shared storage, and it's an important part of the cluster in order to protect data integrity. So as we move these solutions into AWS or onto the AWS Cloud, the key point is that most of that HA capability will work identically in the cloud. Right? It's pretty much the same way as it will work on premises. But there are three challenges which typically need solving as part of every cluster. So the first thing to remember is that some applications will need some form of shared data. Now, this can be provided by a SAN on premises or even an NFS solution on premises, maybe even just a shared disk, but there needs to be some way of sharing data within that cluster. The second challenge we need to solve is that shared block device used for fencing. Okay, so it's that mechanism for turning off machines to ensure that it's down before we do that takeover. And as we record this, there's actually no available shared block device in AWS which we can share across availability zones. So we need to figure out how to do the fencing a little differently. And then the final challenge is around the virtual IP address itself. You can't just take any old IP address, bind it up onto your instance on AWS and expect it to work, right? It doesn't work like that. So let's take a look at the cloud architecture a little deeper.
Thanks, Stephen. And before you start explaining some additional components, how the cluster works within HA on AWS, I wanted to explain a couple of few core concepts. First is an availability zone. It's a discrete data center with redundant power, networking, and connectivity. And each of the availability zones is considered an independent failure zone, meaning that the failure of one availability zone will not impact the other. And we design availability zones so that you can deploy your workloads into different availability zones and help achieve high availability. A VPC is short for virtual private cloud. It's essentially an Amazon VPC is a virtual network dedicated to your AWS account or your AWS organization. And you can have multiple VPCs in your account, with each one of them being isolated or connected to each other, depending on what your individual requirements are. And when you think of the VPC, think of it as a traditional network that you'd operate in your own data center. You need to define the CIDR block. And in this example, the CIDR block is a 10.0/16 network with the availability zone 1 and 2 each having its own /24 network. Now, this is important because a subnet cannot span an availability zone. Stephen?
Yeah, thanks, David. That's great. So this is a typical architecture that we'll see for a cluster running in AWS. And as David's pointed out, we've got a node in each AZ making use of that AWS capability to increase the availability of the overall service. But on the previous slide, we had three challenges that we needed to solve. So let's have a brief introduction to how we solve those. So the first one was that shared application data. So to solve this problem, it's pretty much the easiest one to solve in AWS, and that is to use the EFS service. So you can create a number of endpoints or mount points within each availability zone, connect those local nodes up to that NFS resource, and then you have a highly available service for all your application data. As for the other two problems to solve, things will get a little more complicated. So one of the things that we need to solve is how to manage that virtual IP address. Okay, again, as I mentioned previously, we can't just bind up an IP address and expect it to work. It's not like your own data center where you own the networking layer. It works a little bit differently. You'll also see, again, as David has mentioned, there are the two availability zones have different subnets, and we need something that will work across those two subnets as well. So in this architecture, we actually use something called an AWS overlay IP address, and we use the routing tables to solve this particular problem. So the overlay IP, it's an IP address. It sits outside of the VPC, and AWS will route traffic within that VPC that is destined for that overlay IP address. It will route to one of the two instances in the cluster. The route it takes is specific to a specific node based on whatever the routing table is set to. And anytime the VIP needs to move to a different instance, we need a process to do that. And David will cover that as we get to the next section. The next thing we need to think about is fencing. So again, as I mentioned, there's no shared block device available in AWS across availability zones. So we need to use a different AWS native capability in order to solve the issue. So in this case, we actually make use of something called the AWS API framework in order to power off or fence nodes that we don't want up anymore. And again, we'll look into the detail about how that happens over the next few slides. But one final thing to note is this, and that all these services, the fencing service and the IP service, they're all wrapped by the IAM service. Okay, so there are a number of IAM policies which you have in place, which will give each role the permissions to power off or restart nodes in order to fence or update the routing table. This means the cluster nodes, once assigned this role, means that the SUSE HA Stack on that instance will have permissions to invoke all the necessary actions. What I'll do at this point is hand over to David just to cover this in a little more detail.
Let's start off by explaining what an ENI is. Each Amazon EC2 instance has an Elastic Network Interface, or ENI. In short, it's the virtual network adapter. With that being said, let's look at the top image on the slide. What we're looking at is a screenshot of the cluster resource agent, AWS VPC Move IP. And I'll explain what it does, but for now, just know that it controls the network traffic that's routed to the active node of the cluster. The second line contains parameters that are specific to that AWS VPC Move IP. The first parameter being an overlay IP address. So all network traffic that is destined for the cluster goes to that overlay IP address. And the actual application that we set up for high availability will respond based off that IP address. Now remember, a subnet from the CIDR block for the VPC cannot span an availability zone. So we can't use an IP address from that CIDR block that's associated to the VPC. So we have to use a different IP address. So the next two parameters are the routing tables for each of the availability zones. And you'll also notice there is an ETH0 interface for the active node. So whenever that resource is on that instance, you're actually using the local interface that's associated, or the ENI associated to that instance. Now, the last parameter on the second line is the AWS CLI profile, and it's used so that the instance can run an AWS CLI command, and the actual command is EC2 replace route. And there's permissions that are specific to that instance that allows the updating of those routing tables. So looking at the second image, you'll see the routing table is referenced in the parameters. You'll see the 192 IP address, that's the overlay IP address, and it's not part of the CIDR block. And it's associated to the ENI that is running on the active node. So all traffic destined to the overlay IP is being received by the Amazon EC2 instance based off that routing table. And also, just before we move on to the next slide, the CIDR block for this example is a 10 network. And you can see that right below the 192 IP address, the overlay IP address. So in the event of an issue, or if you're performing some sort of maintenance and promote the passive node to the active node, the AWS VPC Move IP resource agent will start on the passive cluster node. And the resource agent will actually perform an update and change the ENI associated to the overlay IP address. And it's using that ETH0 on the promoted cluster node. And what this does is it allows all traffic that's being routed to that new node within seconds once that table has been updated. And I know I'm repeating myself, but it's important to understand that the overlay IP address is not part of that VPC CIDR block. Because remember, that CIDR block, that subnet, or that specifically that IP address, could not span multiple subnets across availability zones. Looking at the next slide. So let's start out again by looking at the top image, and once again, it's an image of the EC2 fencing agent. The first line does show it's EC2 fencing agent, and it's not using an SBD agent. Now, remember at AWS, as Stephen said, we do not have a shared block storage device that can span multiple availability zones. So we had to come up with a different sort of agent in order to fence another active cluster node, or in order to fence another node. So still looking at that first image, looking at the bottom line, it contains the required parameters for that fencing agent, with the first parameter being a tag. The second parameter is the AWS CLI profile that's set up so that the instance can shut down the members of the cluster if some sort of fencing event is detected. Now, the tag that's shown is a key value pair that's associated with your cluster. Now, the key is used to restrict what instances can be shut down by the IAM role. So looking at this example, any instance with the key launch wizard space tag will be able to be shut down by that role, by that AWS CLI profile. Additionally, the value that contains the host name of the cluster node is contained in the actual value in that key value pair. So you have the cluster tag, the pacemaker tag, and then you actually have the host name associated in the value. So in the event of any sort of failed communication or a fencing event that takes place, assuming both cluster nodes are running, the cluster will issue a fence. The EC2 fencing agent will retrieve the AWS instance ID to fence, and it uses a host name from the key value pair that we described earlier to match the node with the instance tag value name. It issues that stop instance, which is a clean shutdown. And in the event the instance does not respond to that shutdown within approximately 5 minutes, a forced shutdown will occur. Stephen, any questions or anything that you would like to add?
No, that's great. Thanks for covering that. Okay, so just wanted to move on to a small section on a number of tips that we have for running clustering services on top of the AWS Cloud. So just a couple from me to start with. The first one is around the AWS CLI. So David mentioned that there is a profile that's used by the resource agent, which needs to be set up on the node itself. That's actually very simple to overlook when configuring the cluster, because often the AWS CLI, it's often already installed. So it may have been installed already and configured, but you might not have that profile for the CLI set up. Now, without it, the resource agent might not start, or worse still, it might start but not work when needed. So obviously double check that you have that set up as you build your cluster. The second thing I wanted to cover was around the specific actions and again around the AWS CLI. And that's more around getting to the API endpoint in order to run those commands. So again, for me, it's actually about the route that the traffic takes and which needs to be considered. So if your nodes allow outbound activity and they have outbound connectivity from the AWS VPC via an internet gateway or via an AWS internet gateway, then the route that traffic takes out is relatively simple. However, we get some implementations which will route traffic out via a private connection, which goes via their local data center, which means that there's a lot more networking infrastructure to get in the way. So think about local on-premises switches, proxies, firewalls that are effectively between your cluster and that API endpoint. Now, the reason I bring it up is there are because things like fencing, they're actually resource agents themselves within the cluster. And like any resource agent, they're constantly being monitored and checked for health. And in this case, the health check is the fact that the API can be reached. So approximately every 60 seconds or so, there's a dummy call is made to the API. And if for some reason that check fails a number of times, it is possible for the fencing resource or for fencing to actually go inactive, which means it will be unavailable, which means it will affect how your cluster behaves in the event of a failover. So again, just think about your networking team doing firewall maintenance on premises. That firewall might be down for an hour, which means that in theory, that on-premises activity can affect the way your cluster implementation works and behaves. So again, just something to be aware of.
Thanks, Stephen. So looking at pacemaker tags, the slide states it clearly. The tag needs to be unique per cluster. And actually, it is a region-based setting. So you could reuse the tag in a different region, but we highly recommend against doing that because you really want to avoid confusion. So you want to make the pacemaker tags unique because each cluster needs its own tag name and tag value. And the AWS CloudTrail and CloudWatch, so all of the actions that are taking place, whether it's the fencing agent, whether it's the AWS Move IP, all of those are captured in AWS CloudTrail. And what that does is it provides valuable information when you're trying to troubleshoot or investigate any failures. So you can review the AWS CloudTrail logs and determine when either of those events have happened. Additionally, you can also use Amazon CloudWatch to trigger alerts based on those AWS CloudTrail events. So if there is a routing table update, or if there's a fencing, a EC2 shutdown command that was executed, you can actually choose to receive an email notification, a text, whatever event notification you would like that you can set up through the AWS CloudTrail event, you can actually do. And there's also a blog on the SUSE website that does outline how to set it up. And it's a very common practice amongst our customers.
So to finish up, probably the best way to avoid pitfalls when building your cluster on AWS is to follow the documentation. And we actually have some specific best practice guides for running HA on AWS and building clusters with SUSE there. Now, obviously, it's important to reference those guides to make sure that whatever you build is built on a solid foundation. But it's not just a case of downloading and reading and following them. The most important thing I can stress is that you check back on these documents, because they will change over time as lessons are learned, as new features are added and new capabilities are there. So as a cluster that was built 18, 24 months ago might benefit from a regular review just to check that it's still following the best practices in the latest versions of the documentation.
AWS Launch Wizard for SAP provides an automated deployment method By using the service, you can choose to install your SAP HANA or SAP NetWeaver application stack to include all the AWS services needed to run your environment. Additionally, it ensures you're following the best practice for SUSE Linux configuration settings and SAP on AWS. And once you go through the launch wizard, all the configurations that you selected can be saved and reused for future tests and deployments. And recently, I do want to point out that the AWS Launch Wizard announced support for SAP S/4HANA 2021, SAP BW for HANA 2021, and SAP HANA SPS 06 deployments, all running on sleds for SAP 15 SP3.
So with that, I'd just like to say, if you have been, thanks for watching, and I hope you found the content very useful. Goodbye and enjoy the rest of SUSECON.